Hey, it's Chris, and this is my video for States of Matter for chemistry class. First up is solids and their properties. To start, I have a crystalline rock, and as you can see, it has a solid figure that's not malleable. It has geometric shape because of its ordered molecules, and that's it from the rock, I guess. Next up is a solid atom. It's a little egg holder, and it has a definite shape to it because I can't change it. It has definite volume because when you put it in the water, it'll measure up to the second line, which is its volume, and it consistently does this, and so that's why it has definite volume. You'll see me do this again in the video. And then next, it's non-compressible because the molecules are already so tightly packed together, and yeah, pretty much that's really it for solids. Thank you. Next up is liquids. They have no definite shape as they just take the shape of whatever container they are currently in, as seen with this demonstration of me pouring water into a different glass. Yeah, that. And then next up, I got a bottle of water and then a bottle of air and squeezed them. As you could see, the bottle of air squeezes a lot further than the bottle of water because water is non-compressible and it does not want to compress. Yeah. Next up is a viscosity test between two liquids. On the right, I have Purely Texas honey. On the left, I have Sam's purified water. And then when I pour them into the glass at the same time, you could see clearly the water fills up the entire glass in the time it took for the honey to fill up not even half the glass. This is because honey is more viscous than water, which basically means honey flows a lot slower. Next up is surface tension test with a little paper towel. As you could see, the paper towel is not going anywhere, it's just staying on the top because honey has a lot of surface tension, but with the water, you could see the paper towel is slowly starting to fall into the water. This is because water does not have as high of a surface tension as honey, and that's why you're obviously seeing fallout right now. And yeah, that's pretty much it. Next up is gases. This is just a bottle full of air, but when I pour it out, you can clearly see that there is nothing there. That's because it doesn't have a specific shape, and for my air specifically, it's clear. This is because the bunch of molecules are super far apart. And in this next example, I'll fill up a bottle with air, and I'm squeezing it right here. And as you can see, it squeezes pretty far, and that's because air is compressible. And then the next example is there's air everywhere. It has no definite volume because we can't measure it with anything. And as you may or may not be able to see in this next example, I have a bottle of Febreze and I'm spraying it, and this shows that air diffuses very quickly. And this is because they don't like staying packed together, and they move randomly all over the place. And yeah, that's it. Next up is intra and intermolecular bonds. Here I have many weights which represent the atoms found in H2O. The cheese strings represent intermolecular bonds, they're hard to break, and the salt represents intramolecular bonds, they're really easy to break. And yeah, that's it. Next up, blended dispersion. I'll be showing the effects with a paper towel, water, and a water bottle. So if you put the paper towel in the water and then place it on the water bottle, you'll see it'll stick to the water bottle. But this sticking is only short-lived because the effects of blended dispersion don't last very long. And then next is dipole-dipole bonds. There'll be a list for skip. Yeah. Basically, that's dipole-dipole, anything that's not a hydrogen bond. Yeah. On to question 6 about heating curves. First, here we'll see that the melting point of ice is at 0 degrees Celsius, and if it's held at that temperature for nearly 12 minutes. Then, if we heat up the water, which is this little line thing going up, 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 you'll see that water will start to vaporize or boil, fully vaporizing in around 75 minutes. Now this line here, wait a minute, this line here represents kinetic energy because heat is rising, and that's kinetic. And then this line represents potential because heat is not rising right there. Yeah, that's it. Next up, task 7. For this, I'm using a paper towel and water to show capillary action. In this example, you can see the water traveling up the paper towel against gravity. This is because liquids such as water will rise until the adhesive/cohesive forces equal the gravitational force. Next up is adhesion, I'm using with this glass. As you can see with this glass, there are some water droplets sticking to the side of the glass. This is because it is slightly attracted to the glass with those weak bonds. And then finally is cohesion. As you can see with this water, it's following the same path as all the other waters because of the hydrogen bonds that make them stick together. And yeah, that's basically it. This one will be quick. First, melting an ice cube is endothermic because it's taking in heat to change states. And next up, burning a candle is an exothermic reaction because it's giving off heat by burning the wick. For this one, I'll be explaining viscosity. Here are a bottle of Sam's purified water and a bottle of purely Texas honey. Now, if I'm to pour them at the same time, water will fill up the glass leagues faster than honey ever could, as you could see right here. This is because water has a lower viscosity than honey, which means it can flow quicker. The more viscous the liquid, the slower it flows. That's pretty simple. And the Sam's purified water won, of course, and the honey lost. Finally, for something interesting I've learned about is wetting. Here I have a glass of water and a glass of honey. If I pour the honey on the paper towel, it'll sit there in a glob and do nothing. This is because it has high surface tension. Liquids with high surface tension don't tend to wet things very easily. But, on the other hand, if I grab a glass of water and pour it on a paper towel, you'll see in a second that it pretty much instantly wets the entire paper towel. This is because things with higher surface tension tend to spread out more slowly. Things with lower surface tension tend to spread out very quickly and get absorbed into things faster. And yeah, that's it. Alright, thank you for watching my chemistry video. Feel free not to look at my other videos, but if you want to, you can. Alright, I'm out.